He says, how is the capacitive charging current determined for new designs as well as for converting existing systems to using a neutral earthing resistor? So for that one, capacitive charging current, the main contributor is typically your cabling leading from the source to the gear and from the gear to the loads. And in that case, you can use your cabling data sheets, your SLD and your cable schedule, as well as your site plan to do rough estimates on how much capacitance the cables are contributing. Once you have that capacitance value, you can convert that to a reactance by doing 1/2 pi FC, and then you can divide by the line to neutral voltage of the system to get your charging current per phase. Once you have this value, you multiply that by 3 because you want the total system charging current coming from all 3 phases. So in this case, that's how it's the best way to do an estimate calculation. And there's also another rule of thumb in relation to kVA or kilowatt values. In CSA, is the maximum line to ground fault current allowed for impedance grounded systems 10 amps or 25 amps? For this question, it really depends on the type of system you're specifying. Usually high resistance grounding is at 10 amps or less. When you get to low resistance grounding, anything higher than 10 amps would be allowed. I think the largest one we done was 1500 amps. So there's no limit on the upper side, but it comes down to your feeder pickup levels on your feeder breakers to determine how high are you going to go on the let through current of the NGR. Basically, should the zero sequence current sensors be installed above the NGR or at the ground side to reduce the voltage the CT would be exposed to under fault conditions, potentially requiring very high dielectric strength? So in this case, if you're using a passive CT, typically a 600 volt CT would be okay. We have seen the drawing done both ways, where people have put it on the line side and then the other side where people have put it on the ground side. It doesn't really matter as much unless you're dealing with a CT with connected in series basically with the wire. In that case, then you would have to insulate to the nominal system voltage, and then maybe that would increase costs in that case because you would need an additional level of protection. But usually passive window CTs where the voltage is not impacting the CT, that would be the route to take if you want to put it on the neutral path on the line side of the NGR. What is the difference of Table 17 in CEC 2021 versus 2024? I didn't see any difference between 2021 and 2024, but there was a big difference between 2018 and 2021 when Table 17 was first introduced. Does SIGMA3 has a built-in 48-hour timer? The SIGMA3-C does, yes. But the SIGMA3 that came before SIGMA3-C, that one does not. But we do have an external relay that does the time delay if you do have a SIGMA3 and you need the 48-hour timer. How do system harmonics affect the NGR monitor? So for harmonics, majority of the harmonics are canceling out as they are going back to the neutral, except for the triplen harmonics, which would be the 3rd harmonic, the 9th harmonic, and so on. So in that case, our unit is looking strictly at the fundamental frequency, which is at 60 Hertz. So we're trying to mitigate the impact of higher frequencies in making sure that our readings are accurate on our CT, which is 60 Hertz rated. For level voltage 15 kV or more, how to limit the fault current and max fault current value? What you have to do is you have to do the charging current calculation to determine how much charging current there is in your system. And then you also have to look at your protection scheme and what your ground fault pickup levels are on your feeders and sub feeders so that you know how much let through current that you'd have to accommodate for to make sure that the point of fault can isolate itself without impacting the rest of the system. So for example, if you have an 800 amp LSIG breaker and that G function is acting at 20% of the breaker's rating at 160 amps, you wouldn't select a 100 amp NGR if you know that the ground fault is looking for 160 amps. Otherwise, that G function would never activate. So in that case, you would spec out a 200 amp NGR so that you can get enough fault current discrepancy for that 160 amp G function to initiate. I hope that answers the question. Does your solution detect ground faults in the secondary of VFD, especially for low frequency outputs? What I would say is that we're going to be picking up neutral voltage if there's a fault on the output of the VFD. If usually VFDs are isolated though via their own transformers if they're higher pulse. So we are mostly picking up through neutral voltage rather than current. When a ground fault is detected, requirement to notify of a ground fault in lieu of tripping open the upstream protection device. Yes, you have to alarm the condition of the ground fault, whether you're tripping or not. So in the case of high resistance grounding, you may be having process continuity, in which case you would just alarm the ground fault condition. But if you have a low resistance grounding system, then you wouldn't keep that system running. You would alarm the condition of the fault and also trip the upstream protection device. Can diodes be used in the grounding system? And if so, what would be the best way to use it? We use a diode in our sensing resistor, and that's so that the current from faults don't go through our sensing resistor. But to use a diode at the NGR, I don't think that would be recommended. We have to disconnect within 48 hours, right? Once we disconnect the fault, we are good to restart the machine, right? Or we have to isolate the machine for 48 hours. Please elaborate. So what our relay does is it has 3 contacts. It has a trip contact, an RPF fault contact, and a ground fault contact. So when a resistor fault occurs, we're going to alarm the condition of the resistor fault through the RP fault contact. And then the timer begins, and after the timer expires or 48-hour elapses, then the trip contact sends a command to the breaker to trip upstream if the fault is not cleared. So in that 48-hour window where you get the first signal that an RP fault is detected, then you have 48 hours to resolve the issue while the system is still running. And if you can't resolve the issue while the system is still running after 48 hours, then the trip signal will send a command to trip open the breaker. For a 4160 volt system, 400 amp NGR, the resistance is 6 ohms, right at your lower limit threshold of the unit. Have you had success or any issues with the monitor? So for the application I was involved in on a switching system, we had 400 amps 10 seconds on 2 transformers at the switch yard, and it is very, very close threshold to be at because the percentage change is so minute when you're dealing with 6 ohms that the unit has to be very, very carefully calibrated to accommodate 6 ohms. Even a small change in resistance can impact the ohmic value, and as a result, that percent change is much easier to reach. So what we do with our SIGMA3-C is we have a calibration screen which allows us to get metrics on the conductance in the system. Once we have that, we can determine how we're going to set our open circuit and short circuit thresholds based on our open circuit and short circuit tests that we do to see what the conductance drops to and increases to in both of those tests. Once we have that information, then we set our thresholds to be just within those gaps so that we can still effectively monitor for open and short circuit. We did have initial scenarios where the unit just required calibration. Initially though, it may be going into NGR alarm, but with calibration, we can clear those and still effectively detect open and short. It is mandatory to trip resistor failure in 480 volt / 600 volt high impedance systems. Yes. Is there a way to skip this requirement? There are process plants that trip could introduce a safety hazard. So it does mention that the conditions in which you need to provide an automatic alarm and de-energize your system. Some of these process plants may have gotten exceptions from their authority having jurisdiction to justify keeping the system running beyond a 48-hour period for resistor failure, but for these 480, 600 volt high impedance systems, you have to follow code requirement if you're in Canada and trip within 48 hours. So some of the other clients I have decided to use the max threshold of that 48-hour requirement and try their best to figure out a way to solve the issue of the NGR fault within that time frame as part of their standard operating procedure. They will also have an operation plan to basically protect the system knowing that their main breaker is going to trip. So that might be something to look into on that front. If not, then you may have to contact the authority having jurisdiction to get an exception with respect to your particular scenario. If we are using inductive load for our high resistance grounding, do we use the same ground fault monitoring relay? If you're referring to HRG system and you were talking about monitoring the resistor, you can use the same ground fault monitoring relay. If we're talking about individual loads, I would suggest going to our DSP system where you can monitor the resistor as well as monitor the feeder circuits for ground faults so that you can easily locate faults. Why use 200 amps CT on an LRG system limited to 400 amps for 10 seconds? Some consulting engineers are going to be tripping their system upon 20% detection in a 400 amp system. So that would be like about 80 amps. In that case, they may not need the full 400 to 5 CT since their trip range is 20% of the resistor's rating. Some people use 50%, some people use 25%. That's where the consultants make their decision and we just accommodate accordingly with our offering. But most typically, if I was using an LRG system for 400 amps 10 seconds, I would probably use a 400 to 5 CT just so I can get the full usage. For clarification, do you connect the sensor to the transformer's neutral terminal as that is the closest access you have to the actual neutral start point? We recommend connecting right to the start point because Canadian Electric Code requirements require us to monitor right at the XO point. If all you can access is the neutral terminal, then they may allow you an exception for that, depending on who the authority having jurisdiction is. But yeah, I've seen some instances where they can bridge the gap. The only issue with bridging the gap here is that now we're not monitoring right to the XO point with our injection method, right? By bridging this gap, we're kind of cutting it short and jumping across the jumper connection. So it's recommended to always have two connections to the XO point as per figure 10-B12 in the electrical code. High, the monitor can't not be used for voltage monitor than 69 kV. We can design up to 69 kV. How does the SIGMA3 integrate with the OHMNI pulsing system? So the OHMNI pulsing system is a resistor that we typically offer that includes pulsing. It also has a sensing resistor and CT. So basically 7 wires between the SIGMA3 to the OHMNI pulsing system will allow the SIGMA3 to integrate with the OHMNI resistor. I have a small ungrounded 240 volt 3-phase system to which I intend to apply high resistance grounding via a zigzag transformer. The connecting load is only 50 kilowatts based on the rule of thumb 1 ampere capacitive charging current per 1 MVA of connected load. You're using, is it a high leg delta? No, it was an open delta that you were using. And the open delta, we haven't ever spec'd out one for this. I've heard that at some facilities, the high frequency currents are picked up as harmonics by the protection equipment and the system trips. Have you had any experience with this? Usually the harmonics are filtering out as it leads back to the neutral. The only harmonics that get through are the triplet harmonics, but our CT is only rated for the fundamental frequency and that's where all we're looking at. So we don't really have much situations where those high frequency currents are impacting our system. I mean, for high voltage substations, you can design it. Yeah, so the largest resistor that we've ever built was a 69 kV, 1500 amp 10-second unit. Is the I-Gard relay still capable of detecting a ground fault on an ungrounded system? Scenario 1 on CEC table 17. So right now our relay, the SIGMA3-C, if it detects neutral voltage but no neutral current, then it will indicate that we're in NGR fault situation and a ground fault situation, which will conform to scenario 1. Beyond 69 kV, I don't think we have a capability to monitor that. For clarification, do you connect the sensor to the transformer's neutral terminal, as that is the closest access you have to the actual neutral start point? Yes, if that's the closest connection, then you would connect there. For the short circuit scenario, your high frequency testing current comes back to the sensing resistor, irrespective of if there's a short circuit or not in its path. How does the sensing resistor determine if there's a short circuit or not? It's because it doesn't experience the voltage drop across the resistor. So when we're injecting that high frequency signal and it's going through the shorted path rather than through the NGR, then we're getting the full amount of the signal back. What is the difference between the DSP-OHMNI and the SIGMA3-C? So the DSP-OHMNI is a combination unit that has resistor monitoring and feeder monitoring, whereas the SIGMA3-C unit is strictly for resistor monitoring. So depending on your application, you may want the DSP system, which can give you faster fault locating. If you don't have that many feeders, you may want to go with the SIGMA3-C. And in addition to that, the SIGMA3-C can be used for low resistance grounding, whereas the DSP system is strictly high resistance grounding. What is the frequency of the injected current? That's 4 kilohertz. What is the time rating of the impedance grounding device? The time rating of the impedance grounding device, if it's below 5 kV and less than 10 amps, then typically you would go with a continuous rated NGR. What size conductor wires to the sensing resistor? We're only really seeing like less than 500 milliamps of current, I would say, in most of our sensing resistors. So it can be very small, but you would still have to insulate to the line to, or the nominal system voltage for this NN connection that you're making to the XO point, because the voltage will elevate on the neutral. Will these NGR methods work for delta configurations? For delta configurations, if it's a closed delta, we can implement a zigzag transformer and establish an artificial neutral. From that artificial neutral, we can connect an NGR to ground. And we've been doing that a lot on the coasts where they're converting their ungrounded systems to resistance grounding.